I do. Now, it's not that I've never worked with fish, but there's a very unusual situation in Ontario where I worked with the federal government, in that the federal government gave all the responsibility for fish to the province. So we were not allowed to work with fish, but we worked with the people who worked with fish. So we integrated all of our lower trophic level information with fisheries information. So it's not that I don't know anything about fish. I have a little tiny experience.
Yes, sure.
But coming down here, I've sort of gone in a digression into photo-oxidation of dissolved organic carbon. And today I'm going to talk about what we've learned so far. Some of you may have seen some of the slides I'm going to present again, because not everybody has heard my talk a couple of years ago, and I'd like to make an introduction to dissolved organic carbon and to photo-oxidation. But first of all, I'd like to acknowledge the people who work with me. The most important one here is Marcio, and I would say that I started out this project, but now it is really Marcio and I who run this project. And we get guidance from Chris Wood and Dal, and from Scott Smith, who looks like Santa Claus up there, and from Anne Kamanzi, who's been here a couple of times. But I also would like to thank the students and staff of IMPA, particularly Nazare, who is fighting fires and always makes sure we can do what we need to do. Rogerio, I think he's going to be happy when I go because I asked him some questions, any problems. Reginaldo, who sort of keeps the backup going and the water going and equipment going, and I really appreciate their help. And the way they do it, they're always friendly, never a problem. And I also want to thank Sergio, who's our driver. And he's really made our life here very comfortable, very safe, and he's become a friend. So I think the basis of this work is really the knowledge that carbon is the currency of life. And you've probably all heard that before. What it really means is that the major chemical that goes through all of life is carbon. So you go from photosynthesis of carbon through the food web, and we often stop thinking of things at the food web, but really there's a whole other section where all the detritus from the food web, all the respiration from the food web needs to get processed, by which I mean it is turned to CO2 to the atmosphere, either through respiration or photo-oxidation, or it's buried for some later time when it might be further destroyed. So ecosystem processes are often quantified in units of carbon. So that's why we call it a currency. So what is dissolved organic carbon? Basically, it's a definition set up by a bunch of chemists. It's to include everything that's dissolved and a lot of the colloidal carbon that's in the water column. And so they said everything that goes through a 0.45 micron filter is dissolved organic carbon. And we recognize it as the T color in water. So the brown water, we know it's got dissolved organic carbon in it. Other areas can be totally bleached out by the sun and be white, we don't know, but most of the time it's brown. And we like to study it in the Amazon basin for a number of reasons. One, there are extensive forests, as you can see in this picture, around the Amazon region. And this produces a lot of dissolved organic carbon. Would it be better if we turn the lights off, maybe? Is that too dark?
It's not fixed.
Yes, too dark. It's just, that's good.
And although we've been working on the Rio Negro, which has a very specific kind of DOC, because there's a varied geology, we might eventually end up working in different regions, but the DOC has different properties. And it's a very large river system, so the area available for photo-oxidation is quite large, so it could be important. And it's driven by this cyclic hydrography that you have. So the fact that you have flooding the forest and then draining into the river just really accentuates the movement of DOC in the system. But I thought I'd tell you a couple of facts about the carbon in the Amazon. It was, I don't know if it still is, the largest tropical forest in the world because you have a lot of fires. And in that forest, you have 120 petagrams of carbon, which is 10 to the 9 metric tons of carbon sequestered in the Amazonian forest. every year you export to the ocean 36 teragrams of carbon. So that's 36.1 times 10 to the 12 grams of carbon. That's 40% of all the carbon that goes into the oceans every year comes from the Amazon River. And of that, 62% is DOC. So there's a tremendous output of DOC to the ocean where it can be further processed. But at the same time, you actually export more CO2 to the atmosphere than you export DOC to the ocean. You export 80 teragrams of carbon, which is 0.8 petagrams to compare with the amount sequestered up there. That's from 70% of the Amazonian basin. Now this can be from respiration, it could be from photo-oxidation. It could be respiration on the land, because the water will seep down through the soil and take the CO2 from bacterial degradation into the river as well. On a global scale, the loss of CO2 from rivers and streams is 1.8 petagrams of carbon a year. And you'll notice that's much more important than what we lose from lakes and rivers. So that's another reason it's really important to work in the Amazon. But as an ecologist, why do I want to work on dissolved organic carbon? Well, it is essential to carbon cycling, but we also think it drives the heterotrophic food webs, which are really important in these blackwater rivers for fish production. And for you physiologists, you realize that it regulates the environmental pHs that you study. The color in water affects the light, so the habitat that the fish live in. It complexes metals. It makes the river safer for fish. It also complexes and removes nutrients. However, it can increase the toxicity of organic contaminants. And some of the studies done here have shown that it protects against low pH and ultra sodium flux. All in all, it affects the ecological and physiological effects. They can alter species diversity, species habitat, behavior, productivity, and food web structure. So in the Amazon, what happens is you have these storms that come in over a good part of the year. And you know that the water runs through the forest. There's a picture of water running through the forest I took once upon a time. And when the water runs through the forest, you have a lot of decay going on at that point, and a lot of that water goes down through the ground, as well as back into the river, bringing dissolved organic carbon with it. So you have basically the water coming back into the river, carrying dissolved organic carbon. You have it moving down through the soils where you have microbial degradation continues and you get CO2 and DOC going into the river. You have further degradation here, and you have photo-oxidation at the surface. And that's how you produce the CO2 that goes back to the atmosphere. Well, you talk about dissolved organic carbon, you think, oh, it's a very simple thing. It's actually a very complex thing. It's composed of molecules like humic acids and fulvic acids, which give you your color. And they differ in how much they weigh, the ratios of carbon to oxygen. They differ in their color, their pH. And the degradation of these takes a long time, and it's bit by bit. So it's never a simple molecular thing to look at. It's always this huge complex. And when it's degraded, first of all, they've realized that the sunlight can break certain bonds, like the aromatic bonds that we saw on the benzene rings. And then the bacteria take over and they degrade the next bit. And then more sunshine gets rid of all the smaller molecules that the bacteria produced and sort of reverts it to being a more aromatic type of structure. And you get this back and forth and back and forth. And that's how you degrade the DOC between the bacteria and the photo-oxidation. And if it goes partially, there's a lot of partial degradation, so you have smaller molecules, but it hasn't got to CO2. Or you can get complete photo-oxidation to CO2. And these are some of the examples of smaller molecules that you would get. But we all have to realize that not all DOC is the same, as I was just intimating by the different chemical structures. So DOC, that is, never seen light that is coming off the land is much fresher. It's much more liable to break down in the sunshine than DOC that has been exposed to sunshine already. And then the other thing is, it depends where it was produced. DOC that's produced terrestrially, like in the forest, is actually really good DOC. It supports bacterial production much better than algal breakdown of algal products or soft plants. So these are examples from the literature to show you what I mean. So in Dickey Lake, Ontario, this is through the season, but if we start here, so you have ice on Dickey Lake, and then you start getting melting, and the spring freshet is bringing material into the lake that has never been oxidized before. And so you get faster rates of photo-oxidation. But when you go into the summer, there's not a lot of water flow. It's very dry, and this DOC has been processed considerably, so it does not degrade at the same rate, but it degrades at a much lower rate. And as the rains start to come again, you can see there's a variability, probably with rain events, that's slightly higher than the summer, but not as good as that freshet. So there are seasonal patterns, and we see repeatedly in the literature that it's related to rainfall events or water movement events. There's also the effect of habitat, like what kind of material is going into the DOC. And this is a study by Lapierre and Del Giorgio. And it actually is in Canada, in Quebec. And they sampled rivers, lakes, and wetlands. And what they found, they looked at how much could be degraded by bacteria and how much was degraded by sunlight. So bacteria could do about the same on lakes and rivers, but they really did better in wetland type of DOC. But photo-oxidation was best in the rivers and lower in the wetlands and even lower still in lakes. So we measure different things about DOC. And this one up here is a measure of mass, so the size of the molecules. And here, these are more measures of the terrestrial or highly aromatic compounds. And they can separate out DOC depending on these characteristics. So it just shows you again that there are different kinds of DOC. So how do we study DOC here? We basically measure, as you've seen me for days sitting in that corner, freezing. We measure absorbance profiles from a spectrophotometer, and we measure fluorescence. So we have excitation wavelengths here, and this is the emission at each excitation wavelength. And you come up with these pretty patterns. And basically, these are your humic acids, your fulvic acids, and these are your tryptophan-like and tyrosine-like compounds. So we can separate out different compounds fluorometrically. And we also measure the inorganic carbon and the total dissolved organic carbon. So with the absorption indices, there are a couple of key absorption indices. The one you physiologists know about is SAC340, which is a measure of the aromaticity, and it's protective of the fish against metal toxicity, low pH, that kind of thing. The one I mentioned before was the ratio of 254 to 365. And that gives you an idea of the mean mass of the compounds. And there's one that we've added, which is Ka310. And that's because the work on people studying ROS, reactive oxygen species in the natural environment, have found that the degree to which DOC reacts and produces ROS is related to the absorption at 310. And this is just a general absorption capacity. So this profile here came from the work of the Anhavalis. But there's no way we can process our samples like that here, because this is every 2 nanometers. So what we did is we took where the peaks were, and we ran lines through that. So in our, we do one at 250, 300, 325, and 370, because there's an index in the literature which is done at 370. And we end up with patterns like this. So basically, we sum that area for tryptophan, this area for fulvic acid, this area for humic acids, and we calculate a fluorescence index based on the ratio of these two. And that's some of McKnight's work. And depending on whether the ratio is very low, it means it comes from forests, and if it's much higher, it means it comes from more wetlands or from algae, but it's not teratogenous. And it's very important because this was some work by Tranvik and Bertolson, and they've shown that if you put DOC out that's high in humic material, and then you expose it to bacteria, the bacteria grow much more rapidly than if you do the same thing with lake water that's high in chlorophyll, so it has a lot of algal DOC. So basically, bacteria do not grow as well on algal DOC as they do on humic DOC. So given that background, what's our goal? Well, Dal has helped us set a very broad goal. As you know, he does these things. So we want to put together the different elements of a model so we can estimate annual production of CO2 in the Rio Negro. That's rather a large task. And we need to know quite a few different things in order to do this. So Marcio and I are just gradually working our way through these different things. We basically need aerial photo-oxidation production on a daily basis. And we need to know how that relates to the temperature of the water, the oxygen content of the water, pH of the water, the light patterns, and also the hydrological cycle, because as I just showed you, season will have a large impact. In addition, we're going to need information on seasonal patterns of irradiance and spatial patterns of DOC in the river. We wanted to try to do this in as natural a way as possible. So this is why we've set up this pool, which has Rio Negro water in it. We run all our experiments under as natural conditions as possible. And we've had a lot of problems with the chiller. It turns out this isn't such a bad thing. Because on the transect we did this year, you have these are different depths, so that's just below the surface, 0.3 meters, 0.6 meters, 1 meter, 2, 3, and 4. You can see that most of the river sits about 31, just over 30 degrees. But on this lovely sunny day, the surface water was up above 34 degrees by about 11 or 12 in the morning. And it depended where you were on the river, what was going on. So it matches pretty well what our chiller was not able to do, so we actually have very realistic temperature changes in our pool. So in order to get aerial production, we have to put our bottles or our quartz tubes at different depths. So this is a picture of Marcio with some experiment we just ran with depths, different depths. The bottles are different depths. And we get data like this. So this is the measurement of inorganic carbon produced at different depths. And in comparing it to the literature, you can see that at the very surface, we have about 0.86 milligrams of carbon per liter per day. And that's not far off an estimate by Benelli at 0.93 that he made with his bottles, just sort of half in and half out of the water. And our total estimates for aerial production are quite similar, just a bit higher than those of Remington et al. And these are all what I think of as nearshore production estimates, because sometimes the water is not as clear as it is offshore. So our next goal is to try to get offshore production estimates. But how does this compare? Well, there's a number of people, particularly in the north, who've been looking at aerial production of DOC. And in the Arctic, unlike that paper I sent you that claimed that the tropics had the highest rates of photo-oxidation, in the Arctic, Corey and White have got rates up to nearly 300 milligrams of carbon per meter squared per day. And partly that's because they've got 24 hours of sunshine a day. It makes a big difference. And also, they're looking at carbon coming out of the melting temperature. This carbon has never been exposed to light. And so it's extremely fresh. So that would be the maximum sort of rate you could possibly get. But even in southern Sweden, you have variability. And some of that variability is due to the amount of DOC present, and some of it is due to the clarity of the water, but also to the longer days. In the Netherlands, on about a 12-hour system similar to the Rio Negro, their value is quite similar to what we're finding in the Rio Negro right now. So the other thing that we did is, how far down in the water column does photo-oxidation go? So are we talking about this, or this, or this, or this? Like, what layer is important? So we measured our different indices, and then we plotted them against depth. If you take the log of that, you can determine where it's going to cross the x-axis. And we found that most of our measures were between 9 and 20 centimeters. In fact, most were about 9 to 12 centimeters, so that's not very deep. But when we looked at changes in some of our fluorescent measures, our humic acid, we found that they ranged from 19 to 50 centimeters. Much deeper than total oxidation, much deeper than the absorbance indices. So this is something that nobody's ever really looked at before. And what it says is that light can change the structure of your DOC down to half a meter. Much more, that's really important because that may give access to bacteria for greater degrees of degradation than we expected before. So what about our relationship with light? So far we have data from, I guess last September, where we show a very clear relationship between the rate of photo-oxidation and light. And we need to have more data at the low end because at the moment it seems to cut off at 26 million watts per hour per centimeter squared per day. And we're not quite sure what happens, whether the line will curve because of different wavelengths, or whether there really is a section of light where you don't get any photo-oxidation, which might mean that in the rainy season, you're not getting very much. Oxygen effects. I don't want you to try to look at this too carefully. It's a lot of data. I just want you to look at the patterns. Basically, these are 4 of our absorbance measures at 3 oxygen levels. So hyperoxia, normoxia, and near anoxia. They're done in flint glass and in quartz. And I put this up because it shows the importance of the type of wavelengths we're looking at. Flint cuts out the UVB and the lower part of the UVA. So as long as you have lots of oxygen, you can still get photo-oxidation at a higher wavelengths. But when you have very little oxygen, you no longer get photo-oxidation at low oxygen and no low wavelengths. Where if you've got all your wavelengths present, you can still get photo-oxidation at very low oxygen concentrations. So Marcio came to Vancouver and we did oxygen experiments there. And we looked at the actual rates of photo-oxidation. And we started off trying to fill in that gap between normoxia and near anoxia to find out, did we have to worry about oxygen in our model? And this was because on one of our earlier trips, we'd gone way up into the Pacific Barcelos. And Zoe Gallagher and I were measuring oxygen in the surface waters, and it was 2, day or night. It wasn't determined by photosynthesis, it was determined by the water running out of the forest. And what we see here, it doesn't matter. Your oxygen level can go below 2 before you have any effect on photo-oxidation. And we did 2 other experiments to show that it doesn't matter if you go to hyperoxia, it makes no difference. So we tried to fill in this gap. So we have 1.3 and 2.2. They're not significantly different, but we're getting more variability at 1.3. So I think we're sort of on a cusp at that point. So in conclusion, we do have some estimates of area photo-oxidation. We do have some information on irradiance effects, oxygen effects. But we still have to look at temperature and pH. And we have to key this into the seasonal cycle. So we've been working on some of the seasonal patterns over the last couple of weeks. And just for interest, because I know a lot of you are interested in pH, the transect that we did showed considerable variability in pH, not only across the transect, but down through the water column. So you have pHs of about 5 and then into the 4s as you go across the river. But at the surface, you're going up over 6. So there's a bit of a debate whether that is just off-gassing of CO2 that's in the river, or whether it's driven by by photosynthesis. So we still need to go and figure that one out. So thank you very much for coming, and I hope this has been